Hello everyone. In this video we are going to talk about estimating means and the central limit theorem. So estimating means, we want to estimate a population mean. So we need a good estimator of the population mean. And a good estimator of the population mean is simply the sample mean. You just take the mean of the sample to estimate the mean of the population. The sample means a good estimator because it is unbiased and consistent. Well, what do these words mean? Unbiased means that the sample means are all fairly close to the true mean. They cluster around the true mean. A consistent is that they cluster close to each other. So they're clustering about the true mean and close to each other. So you would expect a bell-shaped curve. Most of them are going to be in the middle. The true mean should be right in the middle right here. Most of it's clustering around that true mean. But of course, because of random sampling errors, you get some that are a little off and further away. So let's now talk more specifically about a distribution of sample means, or the sampling distribution of the mean. This is the central limit theorem. It talks about what the sampling distribution of the mean is. So the central limit theorem says, suppose you randomly select samples of size n from a population, and it can be any shaped population, with the mean, I'm just denoting it as mean in uppercase, and a standard deviation, I'm just denoting as SD in uppercase. So I'm using uppercase SD for a population standard deviation, uppercase mean for a population mean. We randomly select samples of size n, and we compute all the sample means. So let me give you a little demonstration of what's going on here. Here I have an example of where I have the computer randomly generate for me samples of size 60, and I did this 40 times. All right, so I want to estimate the mean. So I'm generating a random 60 numbers from a uniform distribution from 0 to 100. This way I know exactly what the distribution looks like. It's not Bell, it's uniform, but it is symmetric. It can take on any value from 0 to 100, though in this case I am just sticking to integers. So we know then if I have a uniform distribution whose values range from 0 to 100, the mean, which is exactly in the middle, must be 50. So here we have a population with mean equal to 50, and then the standard deviation of this uniform distribution is 29.2. I actually drew up the probability distribution for this discrete distribution because I'm working with discrete data, 0 to 100. I have that way out over here. So all the possible values of the random variable x go all the way up to 100. The corresponding probabilities are all 1 out of 101, all right? So they're all the same because this is a uniform distribution. We know the mean is 50, but even if you do the sum product, you can find the mean. So you know the mean is 50. Then I had to compute the variance. So the variance, recall, is a weighted average of the squared differences from the mean. So I took each value of the random variable, subtracted the mean, and squared it for each of the values of the random variable. And then when you sum all these square differences, then what you have to do is multiply each of these by its corresponding probability. In this case, they're all the same, so they're weighted all the same, and then add them all up to get the variance. So that's why you see here that the variance is the sum product, because it's a sum of the products. It's a sum of the products of the squared differences and their corresponding probabilities. So that was the variance. And so variance was 850, standard deviation is always the square root of the variance, so I took the square root of the variance to get a population standard deviation of 29.2. I'm using Excel as a random number generator to compute random numbers, and you may have noticed just now when I hit enter, I was looking at this, then I hit enter, that all the values are changing because every time you change anything, it will generate new samples. So I have actually 40 different samples, right? I have 40 different samples. Each of those samples is size 60. So 40 different samples, each of size 60. So they're all the same size. They're all drawn from the same population that has a mean of 50 and a standard deviation of 29.2. And then I found the sample means. So I have 40 sample means. Okay, 40 sample means. So this is what's going on when they talk in the central limit theorem about randomly select samples of size n from a population with some mean and standard deviation, and we compute the sample means. Now we want to look at the distribution of these sample means. According to the central limit theorem, it's approximately bell-shaped. Actually, the larger the sample size, the closer to a normal distribution this will get. So if we look at our demonstration here, here are all the sample means, and I created for one particular output. This isn't dynamic and doesn't change with each change in the data, but for one of my particular outputs, I actually found the distribution. I did a quick little frequency table and I got a distribution. So this is the main thing here. From one of the particular samples, this is what we got. Okay, this is what we got from one of our particular samples. And you can see, yeah, it's roughly bell-shaped. It is approaching the normal distribution. If you look down here, here's where I actually have some numerical results depending on every iteration of the random number generator. According to the central limit theorem we just discussed, we should have a mean of 50 and a standard deviation of 3.8. Sorry, I'm talking about standard errors down here, standard error. So 3.8, because the standard error is going to be the sample standard deviation, the population standard deviation, which is in D3, divided by the square root of the sample size. So to find the standard error, which is the standard deviation of a sampling distribution, the standard error for the sampling distribution of the means is computed as the standard deviation of the original population from which the samples were drawn, divided by the square root of the sample size of each of those samples. So according to the central limit theorem then, I should have a mean of 50 for my sample means and a standard error of 3.8, right? So when we go back here, we're going to get roughly bell-shaped distribution. The center of that distribution is equal to the population mean, so in this case 50, and the standard error, in this case 3.8. And this reminds you, standard error is the standard deviation of the sampling distribution. The bell curve we use as an approximation of the standard normal. So the standard normal we call the z distribution because its random variables are denoted with z's. The approximation is a t distribution called student's t, and its random variables are t's. And I actually have an example of that right here. So here is an example of the standard normal, which is in blue, and a t distribution in red. What's interesting is the t distribution is different for different sample sizes. This here is for a sample size of 10. So when we go back here to the central limit theorem and talk about the t distribution, the t distribution is different for different sample sizes to take into account that smaller sample sizes have more variation. Right? According to the law of large numbers, the larger your sample size, the better the approximation. So a distribution of sample statistics computed from large samples will be more accurate, or I should say, or closer to the true value. Hence, the distribution will have less variation, and you will have a smaller standard error, which would then give you a thinner bell-shaped curve that gets closer and closer to the z distribution or the standard normal. But the t distribution takes into account smaller samples have more variation, so it's dependent upon the sample size, so it's different for different sample sizes. Now here's a caveat though. I said we randomly select samples of size n from a population with any shape, any shape. In order for this though to hold, to get good results that the distribution of means is approximately normal, if you do have an original population that is obviously skewed, okay, if it's obviously skewed, then you should have sample sizes of at least 30 for the central limit theorem to apply. So if you know or suspect that your original population is very skewed, get bigger sample sizes, at least 30, although we like to get sample sizes as big as we can usually. So that then is what we're showing here. We have in blue the z distribution, the standard normal. In red is a t distribution, and you can see that the t distribution is thicker in the tails, therefore it's a little fatter and shorter than the z distribution. And that difference is more pronounced the smaller the sample size. This is a sample size of 10. That's actually a very small sample size. If we even go smaller, a sample size of 5, look at how much difference there is. If we go up to say 15, then the t distribution is getting closer and closer to the z. Go up to 20, getting even closer. Here's the 30. Okay, very close. And then when you get to really big ones, we'll just put in 100 here. With your eye, you can't even distinguish the two. So as we say, the t distribution approximates the z, and it gets closer and closer to actually becoming the z distribution as the sample size gets larger. So that is the central limit theorem that tells us the sampling distribution of the mean. And so we use that sampling distribution of the mean then to find confidence intervals or an interval estimate of our sample mean. A sample mean is a single number, so it is a point estimate. We want to know how good is that point estimate. It's a good estimator, but how good is it for our particular sample? Well, in order to answer the question of how good is our point estimate, we construct an interval estimate and call it a confidence interval. It's a confidence interval because it has to be associated with the confidence level, because the confidence level defines the likely middle values of the bell curve. So confidence level defines likely values. And the most common of these confidence levels is 95%. So I'm going to do an example using the 95% confidence interval. And then the area that remains in the tails, after defining the middle 95%, the outer 5% divided equally into each tail is called the significance level. So the tails then are the unlikely values. So alpha, which is what we use to call the significance level, and its symbol is, the lowercase alpha. That's why I'm calling it alpha. If we were using the Greek letters, we'd have a lowercase alpha, which looks sort of like a little a or a little fish. That defines the unlikely values in that bell-shaped curve. So if we're working with a confidence interval of 95%, well, then our significance level must be 5%. Let me draw you a picture, or actually let's go back to our picture over here. And I'll just leave it like this right now. So what we want to look at is what's going on here. So what we got here is, according to the central limit theorem, we have an approximately normal distribution, closer to the standard normal for the larger sample size. In the middle here is at population mean value. Right? In the middle is the population mean value. So I will write mean here. It's the population mean. So write it in uppercase because that's how I'm denoting my population mean. Also called a mu, the Greek letter mu, but the Greek letter mu or mu is this. I usually though just write it out when I'm working with Excel. So here's the mean, t-score of 0. Remember, it corresponds to z distributions, and we know that the mean of a z distribution is 0. So when you're looking at the t distribution, it's 0. But if you're just looking at the distribution without t-scores, it would be the population mean from the population that you selected your samples from. We want to define the middle 95% as the likely values. So here's our middle 95%. When we're working with the standard normal, that's at a roughly 2, right? 2 and negative 2. But with the standard normal, when we go to 2 decimal places, that 2 is actually more accurately 1.96, right? So more precisely, if we give more precision, then for a z distribution, it's 1.96. Now the t distribution, remember, it varies for different sample sizes, so its t-score will vary for different sample sizes. And with smaller sample sizes, that t-score can even be bigger than 2. It will always be greater than 1.96. So a t-score for a 95% confidence interval will always be greater than the 1.96. I mean, it may actually equal 1.96 when you get really big sample sizes, but they got to be, in the several hundreds or whatever. I think it was like 300-400 before you even start getting close to this to 2 decimal places. So t is always greater than 1.96. It can even be greater than 2. If I go back up and change the sample size back to 10, then we can see how things look different here. So notice here's the 2 right there at that standard normal, but if I want 95% for the t distribution, notice that it's a little shorter and fatter. So if I want 95% in here, I'm going to have to go a little bit further out, and the t-score would be something a little bit bigger than the 1.96 standard errors in this case from the mean, right? So this would be the negative, and then here's the positive t-score. It'll be more than 1.96. All right, so it's important to know the sample size. Important to know the sample size. So going back to our central limit theorem then, we see then that if we want a 95% confidence level, that corresponds to a significance level of 5%. And we need to find t-scores for the likely value. So we look for that t-score that separates the middle 95% from the values in the tails. This is what I forgot to show you earlier. So let me go back. So when we're out here, okay, a little bit more than -2, a little bit more than +2, all right, This t-score I was talking about is actually called Tcrit, where critical crit stands for critical, okay? So this t-score here is what we call a critical value. Okay? So it is a critical value. Anything beyond the critical value is considered unlikely, right? Anything beyond the critical value is considered unlikely. So the area in this, those are unlikely values. And remember, for our 95% confidence interval, that would then be the top 2.5%. And then here's our middle 95%, which is our confidence level, because this here is defining the likely values. All right, so that t-score that separates the unlikely values from the likely values is called a critical value. So it's T, and we can subscript crit to say T critical, okay? Of course, it's different for different sample sizes. Notice that it is half of alpha. In the textbooks, they tend to call this T. Here's the symbol for alpha. It's 1/2 of alpha. So the critical values in the textbooks are subscripted with alpha over 2, because here's half of alpha that the critical score is separating. When you have output from Excel, if you do built-in tests and it gives you critical values, they subscript them as crit. So T crit would be a critical value, and the t-score from your data would be a t-stat, as in a statistical value. But in the textbooks, we have T sub alpha over 2 for our critical values. Good. Oops, I forgot to clear. It'll stay in the same frame if I don't clear this off. We need to be able to see when we go back to this other page. So back to the central limit theorem. I've already explained that T critical is different for different sample sizes. And T critical is found using T inverse 2T. So we're doing an inverse function on the T distribution, because what we're doing is giving it a probability. In this case, that probability is a probability of getting an unlikely sample, which is alpha, or 5%. It's divided evenly into 2 tails, so that's what this 2T is. And this degrees of freedom is related to the sample size, and that's how we get different T critical scores for different sample sizes. And when we're working with the distribution for sample means, the DF, degrees of freedom, is 1 less than the sample size. All right. So 1 less than the sample size, degrees of freedom, DF. For our 95% confidence level, alpha is 0.5. So we would find our T crit, our critical value, T inverse 2T 0.05 n-1 degrees of freedom. As I said before, t-score always larger than a z-score, because we have greater variation in smaller samples. When we want to actually construct our confidence interval, we're going to have to find the endpoints by adding and subtracting a margin of error to the sample mean. And I have another video that talks about this in more detail. the margin of error is the difference between the critical value and time, the difference between the mean and the critical value. That distance is the margin of error. But we need to know that distance in terms of how many standard errors is it away. So the t-score, our t-crit here, tells us how many standard errors we are away from the mean when we have a particular sample size and a particular alpha. We multiply that by the actual value of the standard error to get the actual distance from the mean, that maximum distance, which is the margin of error. The standard error I discussed is smaller than the standard deviation of the original population. It depends upon the sample size, so we divide the population standard deviation by the square root of the sample size. Of course, if you're not going to know that when you're trying to estimate, so you estimate your standard error by using an estimate of the standard deviation or your sample standard deviation. Let me go back one more time to this picture and show you the margin of error. So we know that the population mean is right in the middle, and we know that we have critical values just beyond 2 standard errors away. The maximum likely difference is this here, because this is the maximum likely difference from the population mean. So this is your margin of error. That's the margin of error, your maximum likely difference from your sample mean and the population mean. Because the worst case value and still be likely is that you get a sample mean that's just barely in here. And if you want to create an interval around that sample mean that captures the true population mean, then it's going to have to be this wide, right? So if here's my x bar, I got to make a big old interval to capture it. So that maximum likely difference, remember, it all depends on the significance level likely, because that then determines t-crit, because t-crit then is going to define the middle 95%, and that's going to be different for different sample sizes. So this is the margin of error. You multiply that by the standard error, and remember, this whole thing, like this is 3 standard errors away. So you multiply your t-crit times your standard error, and that will give you your margin of error. So I know I'm repeating a lot, but I want to try to get this to stick into your head. So I'm drawing pictures, I'm writing it down, I'm showing you already typed. So this then is what we mean by the margin of error and how it's based on the critical value and the standard error. And we need to know the margin of error in order to find the confidence interval. And once we have the confidence interval, we're 95% confident, right? There's our confidence level, that the population mean, this is the parameter we're estimating, is between, and then we have that left endpoint we computed here, and we need to supply the units, and the right endpoint that we compute here, and we need to supply the units. And just to remind you, when we're saying 95% confident, that means the method will give results, good results 95% of the time. So 95 times out of 100 times, the confidence interval that is constructed will actually capture the true mean, because that's a 95% middle value. So 95 out of 100 times, will actually have a confidence interval that captures the true mean, but then there's that 5% chance based on getting an unlikely sample that we will not capture the true mean. So I hope this explains the central limit theorem, more about the t-distribution, and then kind of a review or a preview on confidence intervals for means. I hope this was useful, and once again, thank you for watching.